Let's go over how to model differential equations with the Anadigm switch capacitor system. All right. You can describe differential equations with op-amp circuits with fixed RC time constants and switch capacitor circuits, which these time constants can be set by changing a clock frequency. All right. Now, many systems such as neurons aren't linear time invariant, and so they're not necessarily a analytical solution to them, and so you end up simulating things. All right. Now, the nuclear decay example is linear time invariant, but we're going to use it as a case study to get started. So, and it has an equation. The amount of nuclear material is an exponential decay of some original amount of nuclear materials, and there's a scale factor. All right. Now, the original differential equation, in time, right, is the derivative of the amount of nuclear material is equal to negative time constant times the original the material at any given moment in time, right? And the n can be the nuclear material in kilograms. So first thing we do is convert it to differential equations. Take the differential, take it into an integral, because integral circuits are less noisy. And so we convert that, and we have an integral from a time integral, so we have to use our dummy integration variable. But this system needs a way to get the nuclear material into it, and so I just add a constant, right? Or add a value right here, right? So I'm integrating n, but now I'm adding a constant. So now if, because it's linear time invariant, I can use the Laplace transform. Now n is a function of s, not t. And if you go through the derivation, you see that you get a high-pass looking type transfer function, right? And so when you multiply by a step function, NO divided by S, which is kind of like dumping all the nuclear material into a container all at once and then letting it decay, you get exponential decay. Now, let's start. Now, we have that equation. We know what we should get, so that we can verify that we know how to make op-amp circuits that implement that. So we go back to our equation where n of t, right, is equal to minus the lambda scale factor, integrating over time plus our input. And, here's a signal flow diagram, which should look familiar if you've had 110, except instead of RC, 1 over RC, you have lambda, and you have the minus sign. So it's an inverting integrator, right? We feed that back in. Since it's already negative, it's negative feedback, and we're taking the output here. That output would actually be the low-pass node and how much material has left, all right? And you can derive that and show that you get the same thing. Now, one thing that we have to do is convert our equation to something that the simulator won't saturate with. And so if you have a megagram of material, we can't have a megagram be represented by a megavolt, right? This system, is plus or minus 3 volts. So to keep it easy, if we can only go to 1 volt, then we can just set 1 volt equals to 1 megagram, right? Now the time scale, right? That's really just omega naught from, different classes, or 1 over tau. And so if we know the nuclear material will be gone after 5 tau, and lambda is set to a value that tau is 20 years, then all the material will be gone in 100 years. We don't want to simulate for 100 years. So what if we set lambda equal to 2500, then 5 tau is 2 milliseconds, and this implies that each millisecond in simulation time is equal to 50 years. All right. Let's implement this in the Anadigm tool. All right. Here's a summer, which is this. Now there is something that it does have a low pass filter associated with it, but the corner frequency at 400 kilohertz, we set that to be so much higher than what we're working on that it doesn't affect it. It's almost like having, if you're familiar with the op-amp gain bandwidth or transfer function, staying below that. And that's what we do. So we're fine, right? This output here is in fact the output. N2 would be the high pass node, right, or the output in question, right? Then it goes through an integrator, which we set a time constant. The smallest we can get is 0.0025 divided by a microsecond. That's where we get our 25 from, right? We've made it inverting, and we set the clock to 250 kilohertz. All right. And sorry, just to double check here. This clock is set at 400K, 4000K, and that's so we can get our filter response. All right. Now it goes through the inverting integrator, and then it gets summed back in. Right. Now this is the low pass node, and I just put an inverting gain stage so that you could see the high and the low pass filter. Right. Now, in order to see the whole thing, it's better to have a square wave. So I have a peak of 1 volt and a differential offset of 1 volt, frequency of 250 hertz. And then we simulate for several periods. I'm doing 8 milliseconds here. And so we simulate. Now, the thing is this is a simulation of the simulation, if you will. This is certainly not going as fast as, right, the circuit should have simulated, you know, in circuit time in milliseconds, and you can see that it's taking time here. Once this circuit is implemented into the Anadigm thing, it will run that fast. All right. Now, if you've set everything up in this order properly, you can save this data, right, as a comma delimited file. Because these outputs are differential, and I read it in with Python. I read that in. The some of the names, they have a lot of spaces that can't be used when you're addressing things. It'll be just easier to show you. I'm sorry, there's construction going on today. So, so if you just open that up, it labels everything time, channel 1, 2, 3, 4, no matter what. That's how Anadigm outputs it. But the spaces in there screw it up. Now you could edit this file, but it's much better in Python. And what I'm doing here is changing the names that won't work for Python programming to something that will, right? And then because it's differential, I make a channel 1, which is the difference of channel 1 and 2, and a CH2, which is the difference between 3 and 4. Read it in, and we plot it. And by doing it this way, I can rerun and save that file, and I don't have to edit the CSV file. It'll run every time. And so here we have the blue line is our nuclear decay, right? Of course, you can't get the step function if you don't reset back to 0. That's why everything is a square wave, right? And so that 2 millisecond time would mean 100 years. That 1 volt here would mean 1 megagram, and you can go from here. Now, again, once this would be implemented in a circuit, it would be simulating that 2 milliseconds would really be 2 milliseconds. All right. And we could make it even faster than that. But I'm trying to stay away from that 400 kilohertz cutoff frequency. In fact, you can see the effect of it, of this low pass filter. Okay, is that if I start zooming in, oops, let's just make sure. So the red and the purple are the high pass response we want. And let's zoom in and notice how it doesn't go up to 1 instantaneously. Takes a while to get there. And that would be the 5 tau of the 400 kilohertz low pass filter. All right. But when we set our tau to be on the order of our 5 tau is 2 milliseconds, and then this 5 tau here is 1,000 nanoseconds. It doesn't have a big effect, right? So you can get away with it. Oops. So this was a relatively straightforward example that you, in a way, already knew the answer and didn't need all this stuff. But if you were simulating a neuron or wanted a real-time neuron, this would be definitely the way to go, or a way to go.